today we are going to have the third talk, and all the four, in fact, the fourth talk was to be given by Dr. Somkumar Sarma, but he had to go to Germany for an official work. So that talk also will be presented by Dr. Sonlal Jain. So in this series, Dr. Sonlal Jain will give all the four lectures, and for all the, after each of these lectures, there will be a questionnaire of MCQ type. You can fill that either immediately, or you can also, these questions are also available on our blog and also on our Facebook, where you can fill it, and you are given chance to fill only once, and once you do that, it will be submitted, evaluated, and those who will have a certificate based on that. So before I hand over the mic to Dr. Sonlal Jain, let me introduce to you very briefly, though I have given his introduction in the last two presentations, that is first talk on atmospheric structures and composition, the two talks, and this is his third talk, but there may be few newcomers, so I will give a very brief introduction about him and his work. Sonlal Jain was born on June 7, 1946 in Isharmand village in Rajasthan. He had his education, earned his BSc, MSc and PhD degree from Udaipur University in 1967 and 1969 and 1974 respectively. Before he was to be given a PhD degree by the Rajasthan University, he was offered an assistant professor's position there, and he taught there physics for 1.5 years, and then he was offered a position in National Physical Laboratory at New Delhi in 1975. He joined there as a scientist, and there he did extremely good work on atmospheric research. He developed several instruments indigenously there, and it will not be an exaggeration to say that he is a LIDAR man in India. He developed differential absorption LIDAR, he developed micropulse LIDAR, he developed heterodyne LIDAR, and installed these in NPL at New Delhi and also at Maitri, the Antarctica station of Government of India. In 2005, he retired as a head of the Radio and Atmospheric Science Division of NPL, and then for 5 years he worked there. He did his research work as emeritus scientist, and after that he has been giving series of talks on atmospheric topics at several places in India and abroad, and including Physical Research Laboratory, where he gave courses to UN students, and that's where some of you have interacted very well with him. And he, in his early research career, was at Jet Propulsion Laboratory of NASA in USA, where he did atmospheric research work. He had gone to Antarctic station 3 times as a team member in 13th team, 16th team and the 21st team to Antarctic, and there he for 21st team he was also the station commander. He has published 70 scientific papers in national and international journals. He guided 4 PhD students for their research work. He has been PI, principal investigator, for several international projects like IFCAR and NCAOR and APN, etc. There is a turning point program in India for science education. He participated in 7 of those programs. He has authored chapters in 8 atmospheric science books. With these few words, I request Dr. Jain to start his talk. Dr. Jain, please.
Thank you very much, Dr. Buzz, giving a broad introduction and nice words about me. Thank you very much, and good morning to every one of you for hearing very nicely the last two talks. And today again I'll be talking on atmospheric ozone, and with a special emphasis on the ozone hole over the pole. So maybe it will be a very cold place over Antarctica, and you will be feel very freezing there when I go to there. So please have a patience, and maybe it will be useful talk for you. So I will maybe give some background about my talk, and that is I will talk about the ozone hole over Antarctic and Arctic also, ozone hole dynamics, and our national physical laboratories activities at MET3 Antarctica from 1981 onwards, and design and development of laser heterodyne system. This we will maybe skip today, and maybe tomorrow we will talk about that. And ozone measurements at MET3 using microtop instrument and other techniques, and some conclusions. The ozone is, as you know, one of the most important constituents of the atmosphere. Although it's very small in concentration, if you bring all the ozone from the stratosphere and troposphere at the ground level and uniformly distribute over the whole globe, the thickness of this ozone will be just 3 millimeter. Just 3 millimeter. Can you think? But it makes a whole difference, because it absorbs the ultraviolet radiations in the stratosphere itself, and it protects us from the harmful radiations coming to the earth, and that's the only component which saves you and make a comfortable life here. The reporting of ozone depletion in general and ozone hole in Antarctica in particular witnessed unprecedented surge of interest in atmospheric monitoring. The Antarctica contamination sources are very distant, far away. The air is very, very well mixed here, extremely clean, and is far removed from the spatial and seasonal changes. It is truly the background to the measurements elsewhere, and so it makes the ideal place for making the measurements over Antarctica. It was the foresight of our Indian former Honorable Prime Minister late Indira Gandhi, who conceived the idea of launching Indian scientific expedition to Antarctica in 1981 for the polar investigations in the areas such as atmospheric, biological, medical, engineering, and communication sciences. Ozone, you can know that it is made up of the 3 atoms of the oxygen, say oxygen atom, oxygen here, and ozone formula is like this, O3. Ozone was discovered in the 18th century. The word ozone came from a Greek word that is ozane, meaning smell. Ozone has a pungent odor. It is produced in the industries by electrical discharges for air and water purification. Most of the ozone, as I talked in my last 2 talks also, that about 90% is found in the stratosphere, which begins from about 10 to 16 kilometers above the Earth's surface, depending on the latitudes. Say from polar regions, it will be up to about 10 kilometers, and in the equator and other places 16 kilometers, and extends up to the 50 kilometer altitude, 52, it may be 55. This region is of the highest ozone concentration, and that's why it's known as ozone layer, which extends over the entire globe with some variation with altitude and thickness. The remaining of the 10% of ozone is found in the troposphere, which is the lowest region of the atmosphere, between the Earth's surface and the stratosphere. Ozone is good as well as bad. It has two causes. If it's in the stratospheric heights, it's good. If it is tropospheric height, it's bad. So without this blanket of ozone, human would be exposed to serious sunburn and potential risk for skin cancers. Excessive ozone in the troposphere can act as an eye, throat, and respiration irritants. It's coughing and reducing the lung capacity and cause chest pain, etc. Excessive tropospheric ozone exposure reduce the crop yield and forest growth also. It also damages the carbon sink role of the vegetation, leaving more carbon dioxide in the atmosphere to enhance the greenhouse effect and potential responsible for the potential global warming also. So human or the anthropogenic activities produced compounds such as chlorofluorocarbons and halides containing chlorine and bromine, which destroy the ozone and have disrupted the fragile atmosphere stratospheric ozone layer over Antarctica and whole the globe also. Ozone depletion over Antarctica occurs during the spring when sunlight returns to the South Pole and the temperatures are still very, very cold. Can you think about the temperature over there during springtime? As in the stratosphere, it goes as low as minus 80 degree or even minus 90 or 100. The springtime great loss of ozone is termed as a ozone hole. This I already covered. So this is how ozone profile looks like, how the ozone varies with height. So say it's very low heights, a very, very low concentration, about say 10 to 15 kilometers, and above 15 kilometers extends like this, and peak is around 25 kilometers, and then it again reduces. And the responsible for this ozone layer here is due to the ultraviolet radiations coming from the sun, splits the oxygen molecule to atomic oxygen, and that atoms again react with the oxygen available there and form the ozone there. So that's why these radiations are there. So that's why its ozone layer is formed, and these radiation cannot penetrate below that. So here the ozone is not due to the solar ultraviolet radiation, but due to the other mechanism. Few characteristics of the Antarctica before I go with details of the ozone. This is so don't chill, okay? Don't feel freezing. This is the most coldest, windiest, driest and ice continent, which is nothing but Antarctica. Its area is about 14 million square kilometers and fifth largest continent on this globe. Nearest landmass is South Africa near Peru, which is near about 65 kilometers. Greatest average elevation due to ice cap is 2300 meters. Highest mountain peak is Vostok Winchon-Mishoff, which is 5140 meters above the surface. 90% of the fresh water, world's fresh water, is locked in the ice cap of Antarctica. 90%. Can you imagine that? If this melts, world's ocean level will rise to 50 to 60 meters from the present level, and you can imagine many countries which are very low-lying areas or maybe near the seas, coastal areas may be submerged in the sea. Lowest world temperature recorded is at Vostok station, Russian station Vostok, which was minus 89 degrees centigrade. Mean temperature in the inland, means away from the pole, The coldest is -40 degree and -40 to 70 degree, and warmest is -15 to 35 degrees centigrade. Can you imagine the winds of the order of 300 kilometers per hour? This is the maximum wind there, and normally in ordinary days 70-80 kilometers per hour is very common there. That I've experienced myself. What is the ozone hole? Is there any hole in the sky? No, nothing. The ozone hole is not technically hole where no ozone is present, but is actually a region of exceptionally depleted ozone in the stratosphere or the Antarctica that happens at the beginning of the southern hemisphere spring, or maybe in the northern hemisphere spring also. So in southern hemisphere it happens in the August, September, October, and in the northern hemisphere is March, April. From the historical record, we know that the total column ozone is less than 200 Dobson minutes, not observed since 1979 or up to 1979. We could not find any time below 220 Dobson units before 1979. It has been established that total column ozone level of less than 220 Dobson units is result of a catalyzed ozone loss from the chlorine and bromine compounds. So it was decided that if the ozone level goes below in any place below 220 Dobson units, then we call it a ozone hole. So it's nothing like a hole, but the depleted ozone area is known as Doppler, this ozone hole that is below 220 Dobson units. The ozone hole is also observed over entire Arctic region, but in the northern hemisphere, but this is not as severe as over Antarctica, which I will tell later on. The history of the ozone. The discoveries of observations indicate how human-made chemicals like CFCs create a hole in the ozone layer over Antarctica each spring, that is during 1970s. The CFCs historically, if you know, was invented in 1920s, and that time these chemicals were known as the wonder chemicals, and they were being used for the refrigerators, foam making, electronic industry cleaning, and all these things. But by the time 1980s, 1970s, they are become most hated chemicals, because these chemicals till in the tropospheric heights, in the troposphere, they don't react with anything. So they are non-reactive, non-inflammable, non-toxic. So they were known as a wonder chemicals. But as they go up in the stratospheric level, due to the solar radiations available, they are split, and chlorine and bromine are released from there, and these are the culprits for the ozone depletion. And in 1970, there is another story where the scientist McDonald first said that, okay, the chlorofluorocarbons are very dangerous and they will create the ozone depletion and also global warming and like this. But he was teased in their conference where he made this statement, and he was so much harassed during conference with lot of questions and like this, that you are talking foolishness. And finally he was so much irritated, and finally he got so much nervous due to the people's comment over there, and finally he made a suicide. In 1912, Antarctic explorers observed of unusual well type of clouds in the polar stratosphere. Although they did not knew the significance of these clouds at that time, but now these clouds are one of the component for the ozone depletion also. In 1956, British Antarctic Survey set up at Helle Bay the observatory on the Antarctica for the International Geophysical Year in 1956 to measure 1957 to measure the ozone using a Doption spectrometer. This Doption spectrometer is nothing but a spectrometer having wavelengths in the region of say around 290 to 325 nanometers, and they take two wavelengths. One is absorbed by the ozone and another is absorbed by the ozone, and the difference between them is used for the calculation of ozone density. And Dobson, it is known as Dobson spectrum because Dobson was the person who developed for the first time this type of spectrometer, and he was responsible for measuring the ozone for the first time. In 1985, a group of scientists, say Professor J.C. Foreman, B.C. Gardiner, and Shankly, published in Nature the springtime losses of ozone over Antarctica. But there is another story. The British scientists say that ozone hole was observed there, but NASA scientists could not report this result. When they saw this paper in the Nature, they rechecked their data, satellite data, and found that they have put a flag in their software that if the values below 200 Dobson units comes, then it should be ignored, maybe due to the instrumental error. And finally, they found that there are a lot of data where the values has gone below 220 Dobson unit, and they agreed with the British people that yes, there is a ozone loss, and then they published another paper about the ozone hole. The possible mechanism for the ozone hole, such as chemical, dynamical, meteorological, solar cycle influences, chemistry of CFCs, and solar polar stratospheric clouds were suggested during 1986 to 1987 by various means. Immediately, all sort of people started to work on the ozone loss using various putting parameters of various parameters in their models to find who is the responsible for that, and finally it came out that CFC is the most influential on this thing. Then in 1995, due to their work, Professor Paul Crutzen, he visited India many times, and particularly, and I have personal contacts also him earlier, Mario J. Molina, who worked at Jet Propulsion Laboratory, I also worked. We used to sit on the same floor, and Sherwood, Rowland for their work and all the three people for their work in the atmospheric chemistry, particularly concerning the formation and decomposition of ozone, were awarded the Nobel Prize in the 1995. Recipe for the ozone loss. Who is responsible for that? How it happens? The polar winter leads to formation of polar vortex, which isolates the air within it. Means the air, ozone-rich air, cannot penetrate this vortex, and also these temperatures there remains very cold during the winter time till the vortex is broken up. So this is one of the condition, vortex formation. So air, ozone-rich air cannot penetrate, and the air inside is isolated from the rest of the globe. The temperature inside the vortex that is cold enough, it can go as low as -78 degrees centigrade, which is critical temperature for formation of the polar stratospheric clouds, which I talked earlier. As the vortex air is isolated, the PSE, persist. Till the time vortex is there, PSEs will be there. So these are one thing is the vortex formation, second is the very low temperature, third is the formation of polar stratospheric clouds, and then presence of chlorofluorocarbons. Then, so once the PSEs forms, heterogeneous chemical reactions means solid to solid and liquids, and solid or gases or liquids means heterogeneous reactions takes place on the surface of the PSEs or polar stratospheric clouds and convert the inactive chlorine and bromine reservoirs to more active forms of chlorine and bromine. I will show a slide how that happens. So as soon as sunlight returns after a long break of the winter, because almost 2-3 months there is no sun there at all. So as soon as, and whole the 24 hours you can see the night only. So as soon as sunlight returns to the air inside the polar vortex and allows the production of active chlorine and initiates the catalytic ozone destruction cycle, and ozone loss is very rapid, means one molecule of chlorine can destroy 10,000 molecules of ozone. How it happens is like this. Principal steps of the depletion of the stratospheric ozone. So first is say halogen sources which we release on the Earth's surface by human activities, and maybe some natural process also, which I told you there were that time 1920s, it was known as wonder chemicals due to their properties of non-toxicity and non-reactive, so there are a lot of good properties, and they were used for the many human comfort things such as refrigerators, ACs, foam formations, electronic cleaning industries, and like that. So these chemicals, halogen sources gases, accumulate in the atmosphere and are globally distributed throughout the lower atmosphere by the winds and other motions. Slowly these sources are transported to stratosphere by the air motions. So these are the steps how it happens. Then these gases, most halogen source gases are converted in the stratosphere to reactive halogen gases in chemical reactions involving ultraviolet radiations from the sun. These chemical reactions cause chemical depletion of stratospheric ozone over the globe. So I will show a slide how much it's affecting throughout the globe, but in particularly over Antarctica, the next step also. So this is up to the, these are the 5 steps where the ozone, how ozone depletes the global ozone over different latitudes. But at Antarctica, very low temperature surface reaches on the polar stratospheric cloud reactions, low temperature surface reactions on polar stratospheric clouds, that is heterogeneous chemical reactions, significantly increase the reactive halogen gases and thereby cause severe ozone loss in polar regions in the late winter and early springtime. And then how these halogen gases are removed, so the lot of they have already done lot of loss to the ozone, and by air containing halogen gases returns to the troposphere where the gases are removed by moisture and cloud and rain finally. So this is how it happens. The depth of the area of ozone hole are governed by the amount of chlorine and bromine in the Antarctic stratosphere. How much of chlorine and bromine is there, that will depend how much area is ozone hole is produced. The ozone hole begins to grow in August and reaches its largest area in the late September to early October. Recent observations and several studies have shown that the size of the ozone hole has stabilized and level of ozone depleting substance has decreased by 4 to 5% since 2001. Due to, we will discuss this also later on, that how these CFCs have been controlled by the international agreement that is known as the Montreal Protocol, and we will come to that. But since the chlorine bromine compounds have a very, very long time of the lifetime of the hundreds of years, the recovery of atmosphere ozone is not likely to be noticeable until 2050. And I will show a movie where it will show that how these things is happening. In this movie, you will see that this is saying the temperature of stratospheric heights, and this is a green line is the reference vertical profile of temperature, and this red line will show you the how the current temperature is changing with time, and this is the minimum temperature obtained. And this slide shows in the barometer type of things the adoption units of the ozone, and this is how the ozone is. This will show the total ozone in the atmosphere, and this will show how the profile of ozone changes with time. Let me play this. I don't know why. Maybe some problem here. So what will happen that maybe it's some problem giving, but what will happen, this ozone level here, the blue is broken, and this will be total ozone here with vertical this vertical profiling, and this will go lows and lows as the days goes on, and finally in September it will at these levels on almost 90% would have been gone. Maybe second slide, let me see second one if that works. Maybe there is problem because maybe I take again from the presentation. So here you see how the from August on September you can see the ozone has already gone here almost zero level, and again in the November it came back to its original values, and similarly you might have seen the how the temperature was changing. And let me take another one so I can remove this. Remove this also. And here you see that is from January how much ozone was there. It was very much completely this one. This was here up to April. This was, and the temperature was in this range here. And as you said in the second one, it says it. So let me go to again to the presentation. So this slide shows these are the all halogen sources which we human activities and natural activities or maybe anthropogenic activities are released in the stratospheric level, and they are slowly go up in the atmosphere, and with the winds and storms. It's distributed all over the globe. So these are the different chemicals, CFCs and halogens and all these things. So these are the, you can say, halogen sources, and they are all ozone depleting substances. And then with the solar ultraviolet radiations, they are converted to the halogen reservoirs such as BrCN2, SCl and ClNO2, and these, when the sunlight comes, they become more active and they react with the ozone in the presence of sunlight and depletes the ozone very seriously. So this is how it happens. These are the, I will not go in detail, but these are the reactions, how the ozone say these type of reactions are involved in the 40% of the ozone depletion, this type of reactions 50%, and this type of reaction say 3%. So this slide shows that how ozone destruction takes place with the chlorine, and here this says the total with the Cl plus O3 makes ClO plus O2, and ClO again reacts with the O2 oxygen atom and it makes Cl and O2. The net result is the O plus O3 gives you 2O2. So that's why the ozone is depleted that way. The second is that the ClO plus ClO makes ClO2, and with the presence of the sunlight, this reaction takes place, and finally 2O3 changes to 3O2. And this is the third type of reaction where ClO plus BRO reacts, and they are very, very little in concentration, so the only 3% of the loss is due to this type of reactions. The chlorine, which is the most responsible for this behavior, is totally locked in the troposphere, is in these resources, and as they go in the stratosphere, then most of the chlorine is in the form of reservoir hydrogen chloride, and next is in the ClONO2 and few amount in the ClO. This color code is shown here, and in other cases with the violet color, and total available ozone remains constant throughout this. So they are in different forms. Now, as I said that the polar stratosphere cloud is one of the component responsible for that, and for that the temperature should be minus 878 or below that. So you can see in the Antarctic region, from May onwards, the temperature has gone below 80 degree, also almost minus 90 degree or even less than that, and up to October it remains like this. So almost 3-4 months the this air here is in Antarctica is isolated from the ozone rich air, and after October when the sun rises, then this disappears. But in the Arctic you can see only few days, from here to here only few days temperature goes below this to form the polar stratospheric cloud. So that's why the reason that the Antarctic ozone hole is very severe, or depletion is very severe, while the Arctic one is not that much. And the reason is that Antarctic is surrounded by the sea all the sides. Well, this is not from the sea, and land is also there, so it's not go that much low temperature. So that is the reason for that. This slide shows how much Antarctic whole area is changing with time. So earlier, hardly few million square kilometers was covered with the ozone hole, and as you say that as much as 30 million square kilometers of area has been covered with the ozone hole, and the ozone depletion earlier was very little, and it has gone as low as 100 Dobson units from 250 Dobson units during the ozone hole period, say from 1981 onwards to 2010. These slides again show the comparison with the Arctic and Antarctic. So Antarctic depletion, you say, is very severe, and it is not that much severe. This slide shows the how globally ozone changes. Say 1970 onwards, say 60 onwards, it's shown that up to 1980s there is hardly any ozone change. But beyond that, you can see that it's changing and goes as low as 4%, and then started to recover also, and now it's almost 2 to 3% below the normal level. And with the so that is a global scenario. And latitude wise, you can see that on the equatorial zone there is hardly any loss in the ozone, and in the northern hemisphere is almost 1 to 2% depending on different latitudes, but in the southern hemisphere you see almost up to 20% loss is there. So the slide video which I saw, that this was the normal values. This is for Arctic, and this is during the ozone hole period, how much loss is there. And this is for Antarctic, the normal values, and this is how it changes with time. So it's 1990 to 2009 average values, and on a particular day, 9th October 2006, you can see here almost whole ozone has gone away. See this one. While in Arctic, it has not happened that much. Then the international communities. This is one of the best example of the cooperation between the international community, scientific community, that when they realize that yes, there is an ozone hole, and that is due to the chlorofluorocarbons, as well as the ozone depletion generally in global level is also due to, so they decided to have a Montreal Protocol, and they decided in 1985. This is a scenario that earlier 1985 they decided to go for the Montreal Protocol, and they made some changes in 1987. It was signed by near about 196 countries, and then there was some amendments to that, how much chlorofluorocarbons should be reduced, emission should be reduced from different countries. So there was London Agreement, then Copenhagen Agreement, Vienna Agreement, then Montreal Agreement again, and Beijing. So amendments and adjustments were made to make the law more and more intensive, to have more reduction in this thing. So finally you can see that earlier this was the scenario, and now the chlorofluorocarbons after 1990s has started to reduce, and it is coming down and down. Maybe by 2020 it will be almost, production will be almost normal. So if there would have been no protocol, then the chlorine might have with years might have changed like exponentially, would have been going more and more. With the Montreal Protocol of 1997, it would have reduced slightly, but not to the level this. Then they made amendment and adjustment in 1990 in London, and according to that, this was the scenario. And then Beijing Agreement and Copenhagen Agreement made such a way that it is coming to almost, by the end of the century, this will be almost to the natural sources. So that is the one of the greatest thing that scientists cooperated internationally and controlled the emission. If the Montreal Protocol would have not been there, the excess skin cancers would have been 500 per million people per year, and with the Montreal Protocol it should have been slightly lesser, but with the Copenhagen Agreement, by the end of the century it will be almost very little in comparison to 500. So that is the whole difference the international community has done with the agreements. And with the agreements, all the chlorofluorocarbons started, say, peaking around 1994, and then started to reduce like this. So you can see everything started to reduce, and by the end of the century this will be at the normal level. How the ultraviolet radiation changes with the change in the ozone. So if there is no change in the ozone level, then ultraviolet changes is almost nil. But as you go 60% ozone depletion changes, then ultraviolet radiation will increase almost 150%. So it is not linearly, but it is exponentially, so that how the ultraviolet radiation will cause the damage if we don't control. So this slide I have already shown you earlier, so there is no need to repeat it. So, and then say if we stop the production of chlorofluorocarbons, then what will happen? You will ask the question, what will happen to our production of the refrigerator, foam making, and other industries where you need the CFCs? So they found a mechanism where they found another components known as halogens, which are almost zero potential for the depleting the ozone. Ozone depleting potential is zero for them, and they are being replaced slowly. And most of the countries has already started the replacement of them. And so the scenario of the ozone recovery is shown here. Antarctic minimum and global like this. This slide again shows how the pre-ozone hole and the present conditions and changes. Various instruments are being used for the monitoring the ozone over the globe. So, Montreal Protocol, in one word, perhaps the single most successful international agreement to date has been the Montreal Protocol, in the words of the Kofi Annan, former Secretary General of United Nations. So this is the one of the most successful agreements. And due to that, every year 16 September has been decided to observe as ozone day in the memory of the Montreal Protocol agreements. This I said that how the ozone is depleting in southern hemisphere at different latitudes, say from 0 to 90 degrees. So 90 degree maximum depletion is there. Then in the how this ozone changes with time, say in August is almost this level, and in October it goes like this. This slide I also shown. These are the areas, how much area in different years is covered by the ozone. So sometimes it's very low, and sometimes it goes almost 30 million square kilometers. This again shows how the ozone level increases during October, minimum ozone, and how the area in millions of square kilometer is covered with this thing. 2002 was a exceptional case. So if possible, I will show another slide. Because I gave in the current science paper where I said the ozone hole is recovering, because I got very high values of ozone here in 2002 in Antarctica, and so we gave a paper, and then later on we found from the satellite that it was not recovering, but due to natural phenomena. Say here, this is the Antarctica, and this vortex has divided into two parts. Earlier, so it was there, and I was sitting somewhere here, so I was in the periphery of the vortex. So sometimes we were getting the ozone hole, sometimes we are not getting. So that's why the confusion that particular day the ozone was very high. So I gave a paper, and then finally find that this was not to the ozone recovery, but it was due to the weather conditions over there. So these are these various activities by NPL, and These are the people attended in different years, and I will go to some questions if you have. There is no video visible. Network problems, so maybe, but when you download my talk from the site, you will be able to see it. Yeah, there was some connectivity problem. Yeah, with the people have this Mr. Jayadev Sharma asked, can we relate solar rotation, solar activity with the parameters of ozone layer? Yes, people have done the analysis when the ozone hole was destroyed and ozone depletion was observed. Then they computed their solar activity versus the ozone depletion, and they found that hardly say solar maxima and solar minima time, hardly there was 1 or 2% change in the ozone, but not of the order of say 90% or 100% ozone depletion to the solar activity. So yes, this type of work has been done already. Yes, you are right that they generated EMTs, but the work has been done, and it has shown that there is hardly 1 or 2% change in the ozone due to the solar activity. Oh, the rocket and satellite. I don't know how much damage. Nobody has done that type of analysis, and how they damage because the rocket passes momentarily there, and I don't think they may cause much difference there. And satellite, so because I don't know how much emission they do there, so I don't know. But no, else maybe somebody has done, but I am not aware about the any work has been done in this direction. Why the caution asks that why ozone hole is present in Antarctica? I said that the three conditions: one, chlorofluorocarbons should be there in the atmosphere; then very low temperatures should be there to make the polar stratospheric clouds. So on the surface of these clouds, heterogeneous chemical reactions takes place, and the chlorine is converted into reservoir gases from the source gases, and then when the sun comes, then this explodes, and chlorine is released or bromine are released, and one molecule of chlorine destroys 10,000 molecules of the ozone. So the conditions that very low temperature, formation polar stratic clouds, and the vortex formations which isolates the rest of the air with the Antarctic region due to low temperature. So these are the conditions and the availability of the chlorofluorocarbons. So that is the Antarctica very severe, and Arctic I said that this is not that much severe because it's locked by the land, not by the sea, and that's why temperature don't go that much high for many days. Why Arctic region do not have ozone hole? Arctic region also have ozone hole, but it is not as severe as that much. It happens in the March, April, but only few days because the PSCs are formed only for few days, as I shown you in one of the slides earlier. Krishna Kumar says that means no, there is now there is no much danger of ozone hole on the earth. Yes, not right. You cannot say that no danger because the lifetime of the halogens which has already been released in the atmosphere are of the order of 100 years. So till these all chlorofluorocarbons which has already reached to the stratosphere or released in the troposphere, which slowly up in the stratosphere, and till they are destroyed, completely phased out by the air and the rain and like these, then and then only you can say that there will be no ozone hole. But it will take a lot of time, maybe around the end of the century you will imagine that yes, it will happen, and in between again hope nothing new happens which supports the ozone depletion like CFCs. Any relation with solar rotation rates? And almost no. CFCs are controlled, replaced, and other factors depleting ozone is very less. Is it correct, sir? Yes, the other the constituents which are being replaced by CFCs has the ozone depleting ratio as low as 0. I have some slides, but if I can go to that slides again, but whether I will go or not, I don't know. So I can show that their potential is almost in the last. I will try to see that slide if I can show you. So depleting potential from the other gases which are being replaced is very low, but gases also, but it will take some. Electromagnetic wave, because all the radiations are electromagnetic waves and they are the responsible for the creating ozone layer. Uh, Hiteshi Bhatt asked, has Himandri station of Arctic noticed any ozone hole? It may have observed if they were there taking observation during that time when the polar stratospheric clouds were formed. So I don't have the information about that. Any more questions? If not, I will go to slides again if possible, and then show that slide. Yes, I can go there. There is slide here. This slide shows the lifetime of various chlorofluorocarbons, their global emission in 2008, how much kilotons per year they are being released, and ozone depletion potential. So they all have, say, if the CFC is 1, it has 82, 0.85, 0.82, like this, and their global warming potential is again very high here. But if you go to the next slide, the halons also has the ozone depleting potential here. This. Next slides, you see here HFCs, hydrofluorocarbons, carbons which don't have the chlorine or bromine or this thing. So they have the ozone depleting potential almost zero, but you can see the global warming potential is very high. So they are the protocol, Kyoto Protocol, which are international community, scientific communities again working, and many countries have signed that. So reduce the emission of these things and also replace them to avoid the ozone depletion as well as the global warming scenarios. So with this, thank you very much, and if there are any more questions, let me see, otherwise we can stop it here. So okay, thank you very much, and maybe you all enjoyed the talk and maybe helpful to you. And again, tomorrow we'll be talking about the different type of LIDARs and my work on the LIDAR also. Thank you very much, and thank you for having the very nice questions. And again, let me acknowledge this